In this video, we're going to discuss the phases of matter and how they relate to the intermolecular forces. So 3 common phases of matter are the solid, the liquid, and the gas. The basic premise for a solid is that you have a rigid arrangement of materials and they stay in position. A solid tends to hold its shape. It has a constant density, where a liquid, on the other hand, tends to have free-flowing molecules that roll around each other. As a result, this does not hold its shape. It has a malleable shape or adjustable shape. However, it still does have a constant density. It also has a constant volume. Even though you can spread a liquid out, if you widen it, it gets shorter. If you pour it into a taller glass, it gets narrower. The total volume of your liquid is constant, even if its shape can alter. Truthfully, if you're solid, your volume is always constant as well. It's just a little more obvious for a solid, as it doesn't really change its shape. A gas, on the other hand, has neither a constant volume, a constant density, or a constant shape. Gases are easily compressible. If we think about a gas, generally, we think about molecules bouncing around a large container, completely independent of each other. What we see as we translate from a solid to a liquid to a gas is more free-flowing and more spaced-out molecules. A lot of times if we think about what's solid, what's liquid, and what's gas just around us, we think of different molecules. But every molecule can be in all of these states. We can have a sodium chloride crystal. It's a solid, but a sodium chloride molten is completely possible, and it's even possible to get gaseous sodium ions and chloride ions. However, if we think of something like water, there's solid water, but I also have a glass of water next to me. There's H2o liquid as well, and, well, there's clouds, which is really condensed, but there's humidity spread out in the air. There's also H2o gas. Any material can be a solid, a gas, or a liquid. What's the primary difference here? Temperature. Water has to be solid if it's below 0 degrees Celsius. It's liquid if it's between 0 degrees Celsius and 100 degrees Celsius. And it's gas if it's over 100 degrees Celsius. Temperature is the difference. If we look for sodium chloride, it's a solid all the way up to around 800 degrees Celsius. And if you really try, you can get it to boil somewhere in the vicinity of about 1450 degrees Celsius. The difference here is the temperature. It took a lot more heat available for our sodium chloride to start to liquefy than it did for our water. The difference there is the strength of the intermolecular forces. Our sodium chloride is full positives and full negatives. They rigidly lock into place. Heat makes the molecules vibrate. They shake and bounce and vibrate a bit more. The stronger the attractive force, the better they hold together. Imagine you had 2 pieces of paper with one small bit of Scotch tape. You start waving it. They might come apart. Put 3 or 4 pieces of tape, you might wave it harder. Put a couple of bits of duct tape on, and it's going to be really hard to get those papers to come apart. The stronger the force adhering the material, the more difficult it is to get to go between the phases. Compared to water, which, while having pretty good dipoles, is still only a partial positive and a partial negative being attracted to the next partial positive and partial negative. As a result, it's easier to break those attractive forces. You don't need to be as hot before they start to break. And so we only have to get up to 273 Kelvin, or 0 degrees Celsius, before water starts to freely roll over itself. It loses its rigid arrangement and begins rolling over each molecule. Then you only have to give it up to 100 degrees Celsius, 373 Kelvin, before it will actually break completely apart and just drift off into space. To make a gas from a liquid, you have to fully separate the molecules, which means you have to break all the attractive forces. At 100 degrees Celsius, there's enough energetic movement in the water to begin breaking molecules completely off of the rest of them. To get our ions to separate, however, we need significantly higher temperatures, 1,350 degrees higher than water before we can get sodium and chloride to break free. And so solid, liquid, and gas represent how strongly the attractive forces are holding together versus kind of the ambient energy that's in the material. At a set temperature, there's so much ambient energy for kinetic motion. The weaker bonds will break more easily at that amount. The stronger bonds will hold more firmly. So things with stronger bonds have to be much higher before they'll start to break. So what kind of interactions then play out? Well, there's a general order. Ion-ion interactions tend to be the strongest, followed by ion-dipole, followed by dipole-dipole, followed by nonpolar. And while you can get nonpolar interactions with dipoles and you can get nonpolar interactions with ions, those can be exceedingly more complex as they don't readily dissolve into one another. An ionic material and a nonpolar material tend to separate, and many dipole materials and nonpolars tend to separate as well, though they are common enough that a dipole-nonpolar interaction can be found and will be a bit stronger than a nonpolar-nonpolar interaction. Depending on if you have a pure material or whether you've got a mix of different materials with different types of attractive forces, we can use that to roughly predict what our material's properties are going to be. However, when we have a pure material, it's nice to know what the temperatures will be at where things are affected. For that, we have things like phase diagrams. While temperature is surely one of the largest components, pressure is as well. We don't think about it changing much because on Earth it's pretty constant. But pressure is squishing things, constantly pressing in on them. This makes things not want to expand, and as we went from, say, liquid to a gas, we need our gas to expand. It spreads out. The outside pressure has an effect on phase changes. Here we see for water, this diagram that relates our temperature and our pressure. For 1 atmosphere standard on Earth, we will cross over from a solid to a liquid at 0 degrees Celsius. And at that same pressure, we will cross over from a liquid to a gas out here at 100 degrees Celsius. Well, we're not always at 1 atmosphere. Say you are up in the mountains, and so your pressure is down at 0.8 atmospheres. You'll actually reach your crossover point between liquid and vapor at a lower temperature. This is why cooking directions on various items will sometimes have a line at high elevations, cook for an extra 10 minutes or something. Literally, it's because whatever you're doing isn't as hot. If you're boiling a pasta dish and it says 12 minutes or 15 at high elevations, the reason is the water was just never as hot. It took longer to react and finish cooking your pasta because it boiled at a colder temperature. The outside pressure can also affect our phase changes between solid, liquids, and vapors. In general, most phase diagrams are going to have your liquid gaseous boundary, your solid liquid boundary, and even a solid gas boundary. It is possible to sublimate and go through deposition, going directly from a gas and a solid. Where the three meet, a particular mix of temperature and pressure, that is the triple point, where that molecule can exist simultaneously in all three forms stably. Now you can temporarily be moving some amounts between other temperatures and whatnot. However, to have them persistently maintain an equilibrium, you must be at this temperature and this pressure. Item of note, this line, our solid liquid line, for most materials, it actually angles towards the liquid, as your pressure goes up, so say you were at some temperature with really low pressure, so you were a gas, and the pressure started increasing, the gas gets compressed, and eventually it becomes a liquid. Think propane in a propane tank. It's a gas in your barbecue, but it's a liquid inside the tank. It's been pressurized. Well, if you keep compressing it, eventually it turns solid. Nitrogen gas will do this, other things. Generally, this is because the more compressed, well, solid tends to be more dense than a liquid. This reduces its total volume. If you turn to a solid from a liquid, you shrink in size, you get a smaller volume, you get a smaller surface, you get less total pressure being exerted. As a way to reduce the strain of that pressure as we go up in pressure, turning solid generally is easier for materials. Water, on the other hand, bends to the left. The most dense for water tends to be liquid at 4 degrees Celsius or so. As you then get colder, it actually starts to expand, and as it turns solid, it also expands a little bit. This means as your pressure goes up, you're actually more likely to turn back into a liquid if you're anywhere near low temps. This is why water is so destructive to art sculptures and mountains and the like. The nose of George Washington and Mount Rushmore is constantly being repaired because liquid water will get into cracks, and then when it freezes, it expands and pushes those rocks further apart, cracking them more. Water weathers things pretty well because of this property. The last bit for phase diagrams is the critical point. When we talk about liquids, solids, and gases, those are not all the phases of matter. Sometimes we hear about plasma and whatnot, but a supercritical fluid, basically you have a gas. All the particles are really energetically moving because it's very high temp, and you start to compress it. But they are so energetic they can't really lock into place. They can't really start rolling around each other and sticking because they just keep trying to bounce free even if they can't. At this point, if you then started to lower the temperature, it would start to look like a liquid, but it never goes through what we think of as a phase change. It never boils or condenses. It just smoothly transitions from one to another. Normally, as we cross over this line, we see crystallization for a liquid and a solid, or we see steaming gas release for a liquid to a vapor. But if you're outside the bounds, it just slowly becomes the other one. There's a lot of neat properties with supercritical materials. We may discuss at a later point. But it's something that we can achieve if we have a higher pressure system and a device built to handle it. It's not something we see in the normal everyday world.